Hello, my name is Jason Woodworth from the CAC's Virtual Reality Lab, and welcome to our presentation of our work on redirecting desktop input to animate cross-reality avatars. In this work, we're giving desktop users more expressive avatars with more human-like motion while they meet with immersed users in VR environments. To do this, we developed methods for redirecting desktop inputs such as eye gaze and pointing motion onto the avatar and evaluated them from a viewer's perspective using a two-phase study comparing different levels of desktop and headset-based avatar control. Our purpose for doing this is to address a current gap in the quality of VR and desktop-driven avatars. As an example, we look to the high rates of learning loss among students using standard remote meeting tools like Zoom or Skype to replace in-classroom learning. Some of this, we expect, may be due to a lack of feeling present in the classroom or a sense of engagement with the teacher that these desktop or phone-based applications just don't allow for. Consequently, some educators, and in fact even this very conference, have turned to existing VR meeting spaces like Mozilla Hubs or Verbella, expecting that this medium will help increase student engagement. However, VR interfaces impose some challenges for teachers, including discomfort after repeated use and limited access to educational materials. These VR meeting tools often provide a cross-reality desktop interface that allows a non-immersed user to meet with their immersed peers, but offer significantly reduced avatar control. When in VR mode, I was able to wave my hands around and move my body freely and naturally, but in desktop mode, I'm reduced to just arrow keys and mouse-based camera movement. To address this, we created a novel desktop interface that uses additional sensors and methods to redirect the user's input onto the avatar to animate it in a way that more closely reflects their intent. Such methods include redirecting gaze based on eye tracking input, redirecting head and hand motions when pointing or drawing based on real human-recorded data, and adding head and hand tracking, all controlled by a priority-based module system and body mechanics controller described in the paper. We also created a version usable without additional sensors, using primarily mouse input for our redirection methods, to show the impact of those sensors and if it's still viable without them. To evaluate our methods, we compared avatars recorded using our two interfaces against recreations of those more commonly found in existing cross-reality applications, namely a VR avatar and a conventional first-person desktop interface. To compare these four avatars, we conducted a two-phase study in which subjects evaluated the avatars from a student perspective. In the first phase, subjects took on the role of students watching each avatar give a short presentation on a different local bird. Combinations of avatar and presentation topic were randomized so as to evenly distribute combinations across all subjects. So for example, one subject might watch our sensors-based avatar give a presentation on the American goldfinch, and the VR avatar give one on the northern cardinal, while others might see those avatars presenting different birds. During this, we used eye tracking to measure the angle between the subject's gaze direction and the direction to the teacher's eyes to get an idea for how much visual attention they were giving the teacher. After each presentation, subjects were given 6 questions, with one simple quiz on the presentation material, a question on how human-like the avatar was, how lively the avatar was, and so on, with the questions being examined in full in the paper. For Phase 2, we wanted to gain a deeper understanding on the perception of the individual motions created by each redirection method. Thus, we asked them to rank clips of each avatar performing greeting, pointing, and drawing motions. After viewing each clip, they were asked to rank them based on preference and strangeness, with the option to replay them at will. We analyzed this data primarily using Friedman test with post-hoc pairwise comparisons. From this analysis, we draw 4 main conclusions. First, when looking at our questions on humanity, we see the VR condition is considered significantly more human-like than the conventional desktop approach. Assuming that students would prefer to inhabit a world with a more human-like avatar, this implies that current cross-reality desktop interfaces are providing subpar quality. Second, our novel interface with sensors is not found to be significantly different from either of these two, but since VR and the conventional desktop differ, we know that it must differ from at least one of them. Looking at the mean score and p-values, we can suggest that it is likely somewhere in between them, and more likely to differ from the conventional. Third is that our sensors-based avatar and the VR avatar attract significantly more eye gaze than the conventional one. The lower average angle for these two implies that subjects spent more time looking at or near them, which we'd consider important for engaging a student. Finally, results from Phase 2 show that our novel interface without sensors still shows improved rankings when performing drawing and pointing motions. Ranking for pointing gives us the clearest picture of an overall rank, with our interface sitting somewhere between the VR and conventional approach. We thank you for attending our presentation and hope that you enjoy the rest of the conference and decide to read our paper. Goodbye.